lecture we continue the discussion on supply chain management. In the previous lecture we introduced two types of supply chain which are called the efficient supply chain and the responsive supply chain. The efficient supply chain is to be designed for what are called functional products, and the responsive supply chain is for the innovative products. We have also seen some ways by which we can classify products into functional and innovative, and we also mentioned that the efficient supply chain for functional products concentrates more on cost minimization, while the responsive supply chain for innovative products would concentrate a lot more on service and delivery. Now we will see some aspects of how we design efficient supply chains, or what are the things that go into creating an efficient supply chain. Some of these are continuous replenishment programs using EDI links for information sharing, capturing point of sale data for updating the forecast, invest in supply chain partnerships on the inbound and outbound side, integrate the MRP or planning systems to benefit from improved data visibility, and develop robust inventory control mechanisms to accurately fix reorder points and reorder levels. We saw all these 5 points in the previous lecture, and the common thread that goes along these 5 points is the reduction in inventory. Now we will quickly see how that happens. Now when we talk of continuous replenishment program through information sharing, we immediately talk about reducing the inventory in the partnering entities. Periodic replenishment systems involve higher inventory than continuous replenishment system, and when we have a continuous replenishment system using information sharing, the buffer also will come down. Accurately updating the forecast would immediately help in reducing the variation in the forecast, and therefore reduce the extent of extra inventory that organizations would hold. Invest in partnerships on the inbound and outbound would also reduce both transportation cost as well as inventory cost, and integrating the various systems would automatically reduce the buffers in terms of inventory that various entities in the supply chain would have. So we can now see the thread in all these points, which is the reduction in inventory and reduction in transportation cost, which would reduce the total cost. Now this fits into our description of efficient supply chains concentrating more on cost minimization. Now we will see how responsive supply chains react and what are the things we need to do there. Accept uncertainty in demand and large forecast errors as reality. We have already seen that responsive supply chains are for innovative products, and innovative products show higher variation or uncertainty in demand, and also the forecasts for these cannot be accurate, leading to higher forecast errors. So we need to accept this and then devise systems which will take care of these, which also implies that there would be slightly higher inventory in these kind of systems to the extent possible, and because the profit margins are higher, the overall profits can be increased even if the amount of inventory is a little high. But what is also needed here is improve responsiveness by cutting down lead times, use postponement strategies and delayed product differentiation strategies, and deploy modular design and product platform strategies. And in all these we will realize that the focus is more on reducing the time taken to produce, as well as to be able to produce a variety. Both postponement and delayed product differentiation are ways by which if there are variety of products, the variety actually happens towards the end of the production process, and for most of the production process the product would be the same up to the point where the product differentiates. Now the advantage of doing that is to reduce the inventory that is there. So delayed differentiation would mean the inventory up to the point where the products look similar, the inventories are smaller and the inventories change when the product becomes different. But more than the change of inventory, it is also easy to manage or bring down the time to produce through standardization, because the product would be the same up to a very significant point of the production cycle. So, the emphasis on the responsive supply chain design is more on cutting down the lead time or reducing the time taken to bring the product to the customer. Postponement strategies, packaging postponement is saving in transportation and to be able to handle different requirements. Some examples are also given. Postponing the assembly, postponing is trying to do it in the end and not to try and do it in the middle, and manufacturing postponement talks about unless the firm orders are received, delay the manufacturing, so that the amount of inventory in the system is also reduced. We come to the last slide in this presentation, which is called supply chain planning framework, where we show the strategic, tactical and operational decisions in the supply chain through a planning framework. And we have already seen several aspects of this. Supply chain location and network design come under strategic decisions. We have seen this in an earlier slide. Supply planning, demand planning, forecasting, operations planning are all tactical decisions, while materials management, distribution, execution, logistics, they all come under operational decisions. We also know that strategic decisions are long term decisions whose effect of strategic decisions are there for several years. Tactical decisions are medium term, they are there for several months or several weeks, while operational decisions are short term and they are there for several days of activity. So, when we start designing a supply chain and we start talking of organizations coming together, now these are the various aspects that have to be looked at. The location decisions, which are strategic in nature, the production decisions which are tactical in nature, the inventory and distribution decisions. Some of the production decisions are also operational in nature. Inventory decisions are both tactical and operational in nature, and distribution decisions are more operational in nature. And the information decisions or information sharing and information technology brings all these aspects together and binds them, so that both inventories that exist in the system and time taken to do an activity come down. If we realize that the organization would make more profit by reducing these two dimensions, which is the extent of inventory in the system and the time it takes to make the final product and get it to the customer. So, these two aspects are crucial and these two have to be brought down, so that the overall cost in the supply chain comes down. There are differences that we have seen between the two types of supply chain, one primarily concentrating on cost reduction and the other concentrating primarily on delivery and reduced time to market. In spite of these differences, if you see that if we bring these two costs together, the cost of inventory and the loss of profit by delaying the time taken to produce, or the gain by reducing the time taken to produce, organizations can benefit and make a lot of profit through proper relationship, which is the essence of supply chain management. We just go back to one of the slides that we have seen earlier, which talks about the major supply chain decisions, which I have indicated 5 of them: location decisions, production decisions, inventory decisions, transportation decisions and information decisions. Now, we go back and see how much of these we have covered in the course and what are the things that are remaining to be done in this course. When we started this course with a lot of emphasis on operations management, as I mentioned, we have spent a lot of time on production decisions, starting from forecasting, understanding forecasting completely to the extent possible, understanding the various models in forecasting, and then we looked at aggregate planning. We saw several models for aggregate planning, and then much later we did scheduling and sequencing, we did little bit of MRP. So, all of these come under production decisions. We have seen several inventory models for what are called cycle inventory and safety inventory, which means models that relate the order quantities and models that relate the reorder levels and safety stocks. So, we have spent some time covering the inventory decisions and we have spent some time addressing the production decisions in this course. Very briefly, we have looked at some aspects of location decisions, and we are yet to look at some aspects of transportation decisions and the role of information technology on the supply chain. So, what we will do now is revisit some of the location decisions that we have seen and continue to discuss some location models that talk about locating facilities and warehouses, and then we will move on to transportation decisions and models for transportation, and then we will look at information systems and the role of information system in effectively making the supply chain performance better. The models that we have actually seen related to location earlier in this course are three models that we have seen. So, we have seen the P median model, we have seen the fixed charge problem, and we have seen location of multiple facilities or location of warehouses. Earlier in this course through the location models. Now, we will see a few more location models and try to link them with this. So, the most basic model when it comes to locating warehouses and retailers for a single product is an assignment problem, where we minimize Dij Xij, where Xij equal to 1 if the retailer J gets supply from warehouse I and gets all the supply from warehouse I. The model that we show here is to minimize Dij Xij. Here we assume that we would have several warehouses and a large number of customers or retailers. So, we call this as warehouse and we call this as retailers. Now, we are going to assume when we look at this formulation that there is a demand Dj from each of these. Now, there is a supply from each one of these Si. Now, we are going to assign each of these retailers to this. For example, we may have a solution where if we have something like this, then we would say that retailers 1, 2 and 4 get their supplies from supply Si. Now, at present we need not consider the Dj's and the Si's explicitly. We would simply say that there are certain number of retailers and certain number of warehouses, and when we actually do up to this, the problem will be to minimize the distance. So, there is a distance dij that we would like to minimize. We also would like to use all these supplies, and then we have to say that each of these retailers will get their supplies only from one particular warehouse. There is a demand for dj for that item from each of these. There is also a restriction that a particular warehouse will not supply to more than a certain number of retailers. So, this would still be related to a typical assignment problem, even though a typical assignment problem in the OR literature would talk about sigma xij equal to 1, sigma xij equal to 1. Now, this can be expanded to a simple assignment problem, even when we put a restriction that this will supply to a maximum of certain numbers. Now, up to this is either directly an assignment problem or can be modeled as an assignment problem. Now, this constraint also becomes important when we bring a certain supply to each one of these, which means there is a capacity here, and then we need to do this. Now, this is not exactly a transportation problem. The difference comes because in a transportation problem there is a supply quantity and there is a demand quantity. Transportation problem does not put an explicit restriction that all the demands have to come through only one supplier. Transportation problem would allow that the demand of this can be met from here as well as here. So, the moment we put an additional restriction to the transportation problem that the demand of this should be met only from one of them, it becomes what is called a generalized assignment problem. So, generalized assignment problem which can be solved through binary programming. Xij takes values 0 or 1 and this can be solved as a 0 1 or binary optimization problem. So, the one of the models is which given a set of warehouses or given a set of supply points, given a set of retailers or given a set of demand points with known demand dj, now which warehouse will supply to which retailer such that the capacity is considered and all the demand of the retailer has to be met from the warehouse, and there is an additional restriction that for reasons of control that this does not supply to more than a certain number of retailers. So, this is a standard problem where we model how the demand of each thing can be met. The second model would be known number of warehouses and retailers, single product, and a retailer can get from more than one source. So, the second problem is a simpler version of this problem. So, we would still have this, we would still say that this constraint is modified. Now, this constraint will be modified to sigma xij is greater than or equal to dj for the retailer j, and sigma xij is less than or equal to si, and this does not exist, this does not exist. Xij is not binary anymore, xij is the amount of demand or quantity that is met from transporting from I to j, and it becomes a straightforward transportation problem. This does not involve dedication. For example, here in model 2 we do not assume that all the demand is going to be met from only one. You may have a situation where the demand of this can be met from both these. So, the model 2 is actually a simpler version than model 1 in terms of assumptions, where a retailer can also get from more than one supply, and in terms of solution because it becomes a straightforward transportation problem which is simpler to solve than the generalized assignment problem. Now, having seen those two models, we will now come back to first the P median and then the fixed charge, and then we will go to the model where we talk about, which is called the fixed charge transportation problem, and I will explain the difference between them. So, though I have shown this as model 3 in this PPT, after the model 2 we need to look at P median as well as the fixed charge problem. We have already seen P median and fixed charge in an earlier lecture. So, I will just provide a very quick recap of both of these before we go to the next one, which is called the fixed charge transportation problem. P median, one of the ways of introducing the P median problem is to say that there are points here. Let us say there are 6 points or there are 6 customers, and now let us say we want to locate say 2 factories or known number of factories or P factories or P medians. Now, which of these 6 will be the medians such that if for example these 2 are the medians. Now, first let me describe this problem mathematically, then I will describe this problem with respect to the context in which we are looking at it. Now, there are 6 points or there are n points. There is a distance matrix Dij that is known, which means the distance between each of them is known. We call these as 1, 2, 3, 4, 5, 6. Distance between a point and itself is 0. So, the Dij matrix is known. The P median is to choose P out of these n points, there are n points, to choose P out of these n points which act as medians, and the remaining n minus P, each of these points is attached to a median. For example, if we choose these 2 as median, then these 4 are the non-median points, and each of the non-median point gets attached to a median point. For example, this might get attached to this might get attached to this would be attached to this would be attached to this, such that the sum of these distances is minimized. There will be 6 distances. Now, these 2 points attach to themselves, so their distance is 0. These 4 points are going to get attached to a median, so there will be 4 distances. Now, which are the 2 medians, the best 2 medians, and to which medians the non-medians get attached, such that the sum of the distance, the 4 distances is minimized, is called the P median problem. Now, what is the relevance of the P median problem in the context of what we are looking at? Now, we could say that here are 6 customers. Now, we want to establish say 2 factories, P equal to 2. We want to establish 2 factories such that we are able to meet the customer demands based on distance. Now, we want to find out the best location out of these 6, the best 2 locations out of these 6, such that the remaining 4 are allocated into the 2 locations and the distance is minimized. So, that is the relevance of the P median problem in the context of what we are looking at. So, there are 6 customers and we want to who are located in 6 different places. The Dij matrix is known, and if P equal to 2, which out of these 6 locations, which 2 out of these 6 we would locate a factory, and these 2 located factories will cater to the requirement of the 4 remaining points. Now, which of these 4 remaining points are attached to the factory is given by the P median problem. So, we have seen ways to solve the P median problem, which is our next location model. Now, the fixed charge problem, automatically it can be seen as a logical extension of the P median problem. It can also be seen in a slightly different context. Now, when we extend this P median problem and then we start saying in the P median problem we are going to assume that whether I make this one as a factory or this one as a factory, the cost of making this as a factory is the same across all the points. Now, in the fixed charge I am going to give an Fi, which is the fixed cost of making a factory from this location. So, the problem changes to Fi Yi plus Dij Xij. So, there is going to be a fixed cost. Now, the other way is there can also be a capacity of this, which I may call as Ci or capacity of I, Now in the P median we have not included costs and capacities. Now suppose I solve a P median and for example let us say these are the two best locations and these two are the things, then at the end of the P median I would say locate factories here based on distance, the individual cost is going to be the same. Now if the demands are D1 plus D6 plus D5, then it is necessary to have a capacity of D1 plus D6 plus D5 here and a capacity of D2 plus D3 plus D4 here. Now in the fixed charge we do it slightly differently, we start defining what the capacities are going to be and then decide which are the two best locations and how the demands of the rest of them are going to be handled by this. Fixed charge does not, again there are two ways of fixed charge, where one of the ways is to say that if there is a factory located here and this one does not get a factory, then all the demand of this should come only from one of these, either this or this, which is the P median kind of assumption. But in practice we could say part of the demand can come from here, part of the demand can come from here depending on the capacities of these two places. So fixed charge can be seen as a logical extension of P median, where there is a fixed cost of creating which is different for different points, as well as the capacities are predetermined in the fixed charge, whereas in some ways they are post determined in the P median, they are already given to us. And the difference is fixed charge does not necessarily restrict that all the demand should come from only one of the chosen factories. Other way to look at the fixed charge problem is to say here are some potential sites for the factories and here are the customers. So in this way of introducing the fixed charge problem, we are not going to locate factories in customer locations. Now the specific sites where factories are located are different from the customer sites. Therefore this as a graph is a bipartite graph. So there is no connection between or amongst these or amongst these. Now again the Dij's are now like this and so on. So here the Dij will be a square matrix. If there are 6 points we will get a 6 into 6 Dij. Now here if there are 4 sites and 6 customers, the Dij matrix will be a 4 into 6 matrix. Then we want to find out which two of these we select. There is an Fi, there is a Ci and there is a Dj. So we have seen some aspects of P median and we have also seen some aspect of the fixed charge problem in an earlier lecture. Now with this background we move to model 3, which talks about warehouses and retailers. We will visit this location of warehouses later. So this model talks about warehouses and retailers, where we have a known number of warehouses and retailers. We are talking of a single product. We also say that the retailer can get items from more than one warehouse and there is a fixed and variable cost of transportation. So the important change is that there is a fixed and variable cost of transportation. So let me go back and explain this through this network. Now here we have a set of warehouses and then we have a set of retailers. Now the question is, there is a supply Si in each one of these. This is not a location problem per se. The decision here is not where to locate. In a P median the decision is where to locate, in a fixed charge the decision is where to locate. Now here we assume that there are a set of warehouses, there are a set of retailers. For the sake of illustration there are 4 warehouses and there are 7 retailers. Now each one is connected to every other, so it means every warehouse can supply to every retailer. The normal transportation problem, which was our model 2, talks about there is an Si, there is a Dj. How much do I send? Assumption is this can be met even partly from here and partly from here. The additional dimension in this problem, if you look at the objective function, the old transportation problem will have Cij, Xij, and now we also have another Dij. Oh, here we have Cij, Yij and Dij, Xij. So, there are two terms in the fixed charge transportation problem, whereas in the old transportation problem there was only one term, which is dij xij. Xij is the quantity transported from I to j. Now, we introduce a yij and say that if, for example, I transport a quantity x11 from the first supplier to the first demand, now the cost of transportation will be d11 x11, but there is an additional cost which is called a fixed charge of doing this. Now, this fixed charge would be like an additional toll that I may have to pay if I choose to transport from this to this. So, there are two decisions. First of all, whether I choose to transport from I to j, and then if I choose to transport from I to j, what is the quantity that I transport from I to j. Whether I choose to transport is given by the yij, and the quantity that I transport is given by the xij. So, the constraints will be that each sigma xij is greater than or equal to dj, whatever comes into this will meet this demand, and as far as the other one, sigma xij is less than or equal to si and yij. We could there we have shown it as two different constraints. We have shown two constraints, which is xij less than equal to si, and then said xij less than equal to myij. They can be brought together into a single constraint, which will say that this supply or capacity of si is available only when, to meet the requirement of a j partly, only when we choose the route ij. So, only if yij is 1, this in whole or part is available for this. So, this is the constraint. Yij will be binary and xij will be a quantity. So, this is called fixed charge transportation problem. It is different from the fixed charge problem. The difference comes from the fact that in a fixed charge transportation problem, there is a charge, fixed charge Fij between I and j, whereas in a fixed charge problem there is an Fi associated with this I. Now, in the fixed charge problem, the fixed charge is for a node, and in a fixed charge transportation problem, the fixed charge is for an arc or an edge that connects I and j. Here it is for a node or vertex, which is I. So, there is a cost associated here, there is a cost associated here. This cost should be seen as cost of setting up a facility, and this cost should be seen as a fixed cost of transporting, which is like a toll that is paid when you move items from I to j. So, that is our model 3, which talks about warehouses and retailers. Then we move to the fourth model, which is the capacitated plant location model, which is actually the fixed charge problem. So, Fiyi, so this is what is shown there as model 4, which is the fixed charge problem. Now, you see that the objective function is sigma Fiyi plus sigma Cij xij or Dij xij. If this is a generic expression which talks about the unit cost of transporting from I to j, we could use Dij xij if the unit cost is proportional to the distance and the proportionality is 1. For example, it costs 1 rupee to transport a unit distance, then you can use Dij xij or Cij xij. So, we have already seen some aspects of the plant location or a fixed charge problem earlier in this course. Now, we look at locating plants, capacitated plant location model with a single sourcing. So, as model 5, what we see is something like this, the same fixed charge problem here. So, when we go back to this network, which I draw again, these are the possible sites, these are the customers, So, there is an Fi associated with this site, there is a Dj associated with this customer, now all that, now we have to Fi, so yi equal to 1 if this site is chosen. So, the objective function will minimize, this is the cost of location, this is the cost of allocation. So, it is also called location allocation problem, because we talk of locating facilities as well as we talk of allocating from the capacity of these facilities, allocating to meet the demand. It is called location allocation problem. So, all the demand should be from only a single place, that is why we call capacitated plant location with single sourcing, which means the demand, entire demand of this will be met from only one of these, and that one has to be chosen. So, you will have a constraint which will say sigma xij equal to 1, which means in this model xij is binary, ya is also binary, ya is 0 or 1 if we choose this, if it is chosen it is 1, if it is not chosen it is 0. So, whatever is chosen will incur a fixed cost which is Fi yi. Now, the demand of all of these have to be met. So, xij equal to 1 if the demand of this j is going to be met from a chosen I. Since xij equal to 1 will ensure that the demand of each of these is met from only one of these. And the second thing that we need to look at is sigma dj xij is less than or equal to ki yi or ci yi. So, not only this gets the entire demand from one of them, this should get its demand from a chosen site. So, if this site is chosen, then yi will be 1, only then it will get from this. If this is not chosen, this cannot supply to this, and if this is chosen, this has a capacity of ci yi. So, whatever you get from this capacity should also be within what this supplies. So, this ci yi is the capacity of the chosen one, and this is given to several dj xij. So, the capacity is greater than the demand. So, the single constraint takes care of all of that. The objective function changes because xij is binary. So, dj xij is the demand. So, cij into this. So, cost into demand. So, this is called locating plants capacitated model, because ki or ci talks about the capacity of this when it is chosen. So, it is capacitated. Single sourcing, because all the demand from here is met from only one supply point. So, that is our model 5, which is capacitated plant location with single sourcing. Sixth model is locating plants and warehouses simultaneously. Now, this model is exactly the same model that we have seen here earlier, where we have spoken about locating plants and warehouses simultaneously, which means we are looking at multiple stages. So, there can be a stage where we have plants or factories, there will be a stage where we will have warehouses, and there will be a set of customers. So, the question here is, we can put a restriction on the number of factories that we wish to locate, we can put a restriction on the number of warehouses that we wish to locate. So, we will have multiple decisions Fi yi. So, Fi would be a fixed cost here, yi will be the decision here, and then we also have another one Fe ye. So, this will be fixed cost Fe, and then we would possibly have another ye or a z or whatever variable we can use. So, if we choose some of these. So, there is a fixed cost of location here, there is a fixed cost of location here. Now, the moment there is a fixed cost of location here, there is a capacity. So, things have to be produced and transported only to chosen facilities. because there is a cost of creating this. Then these are transported to the chosen facilities, and from there they are transported to meet the requirements of these customers. So here again we could have a dedicated or a single sourcing model or a multiple sourcing, where a chosen warehouse can supply to either, or the other way, a demand is met only completely from one warehouse or can be met from multiple warehouses. Now there is a distribution cost here, there is a distribution cost here, there is a fixed location cost here, there is a fixed location cost here. Therefore you will see 5 terms or 4 terms or 5 terms in this, depending on the number of layers. And if there is one more layer here, there is a warehouse, distribution as well as the customer, then you have one more transportation cost. The location decisions usually concern only this and this: how many plants to locate, how many warehouses to locate. Rest of them are transportation costs and linking constraints, which will link the capacity as well as the demand, which is shown here 4 layers. So there are 3 types of distribution costs. We could also look at more advanced location problems, particularly for multiple products. So far the models that we have seen are largely for single products, and now these can also be expanded to looking at multiple products and fixed toll. So you get a much more generic formulation, which is shown here with Cij k Xij k, where k represents a product or a market, I to j would simply mean from the plant to the customer. So here we are not looking at multiple layers in the supply chain, we are talking about a set of factories and a set of customers and multiple products or multiple markets. There is a location, there is an allocation, and there are some linking constraints for each one of them. Now we will look at a couple of more aspects, which are called warehouse aggregation and safety stock and service levels in this. Now what exactly do we mean by warehouse aggregation? Now when we look at a model like this, when we look at all our location and allocation models, now let us see this. There are times when we have, let us assume there is a warehouse here and there are several customers here. Now there are times we wish to make another decision which says, now can we actually have 2 warehouses? For example, can we have one warehouse here and we have one warehouse here? Now if we replace this central warehouse with these 2 warehouses, we realize that the distance travelled will be less, because here we are looking at these 6 distances, whereas here you are looking at essentially 3 distances. If this merges with this, we are looking at 3 plus 3, we look at 4 distances, and it will be much smaller than the sum of the distance here. But now what are the advantages and the disadvantages? Now the advantages and disadvantages, the advantage is in reduced transportation cost, the disadvantage could be more inventory or buffer needs to be kept here as well as here, whereas when we centralize them and bring them together, the inventory that we will have there will be much less. So there is this traditional trade off between a centralized warehouse where the inventory is kept, the safety is less, transportation costs are more, decentralized warehouses where the transportation costs are less and the inventories could be more. Now we look at some of these, we look at a single warehouse and multiple retailers. Now one could simply easily calculate the economic order quantity cost for each retailer for n retailers. So if we have n retailers, using our traditional formula that we have used, the economic order quantity Q will be equal to root over 2 D C naught by Cc, where this is the demand for the item, this is the order cost, this is the inventory carrying cost. So for each of them, this will be, for a single item, this will be the economic order quantity, and the total cost at the economic order quantity will be root over 2 D C naught Cc. Now, if we have it for n different retailers, the total cost there will be, for n different retailers, n into root of 2d C naught Cc. Now, if we bring all of these together into a central place, then the total demand will become n into d, and therefore, the economic order quantity will be root over 2 n d C naught by C c, and the total cost T C 2, if we may call this, is equal to root over 2 n d C naught C c. Now, this is smaller, less than T C 1, because n into root of 2 d C naught C c will be bigger than root over 2 times n d C naught C c, and now there is a saving in the total cost if we bring it down together, and the same thing can be seen as either warehouse aggregation or can be seen as inventory aggregation for a set of n retailers and so on. So, the saving will come down, and this saving can easily be shown as 1 over root n by n, or 1 over 1 by root n, or 1 over root n by n will now be the saving when we try and bring the warehouses together. The other aspect that we can see is also the saving in safety stock and in service levels, which we have actually seen in an earlier lecture on inventory. Now, we also know that if each one of these retailers, there is a lead time demand distribution, and if sigma is the standard deviation of the lead time demand, and then we have a service level SL, and based on this service level we go back to the normal distribution and then find out a Z from the normal distribution. Now, Z sigma is the safety stock that will be maintained. Now, for n people we will have n into Z sigma in each of these places, whereas when we pool them together we have already shown that the standard deviation when combined together is actually root n into sigma, and the same safety stock, the total amount of safety stock maintained if we bring them together will be Z into root n into sigma, whereas if we maintain them in different places it will be Z into n into sigma, very similar to n into root over 2 d C naught C c and root n over root of 2 d C naught C c. Similarly, n into Z sigma versus root n into Z sigma. Once again it is possible to show that the saving is of the order of 1 minus root n by n, or 1 minus 1 by root n. So, the advantage of doing this from an inventory point of view is to try and aggregate it, or try and make decisions which are for everybody together, which is an essential dimension of supply chain, because if the individual players make their own decisions, or if the individuals have their own warehouses, the amount of safety stock will be higher and the total cost of inventory will be higher. So, by centralizing and by bringing them together, the total cost of inventory can be brought down. But we have already seen that in some ways the cost of transportation will increase when we try. The cost of transportation will be lower if we have different different warehouses rather than a centralized warehousing. The important aspect is for these organizations to come together and to be able to do centralized ordering or to be able to take from a centralized warehouse. So, the inventory cost may go up a little bit when you centralize it and take it from a centralized warehouse, but the total cost can come down. Much later we will see that by proper information sharing we can actually bring down even the cost of transportation by aggregating or when we aggregate the demand. So, with this we also look at some models for warehouse and models for warehouse aggregation, and what we have seen now along with what we have seen earlier in terms of the P median problem, the fixed charge problem and location of factories and warehouses would give us a good picture of the location decisions with respect to a supply chain and the ability to bring down the total cost through aggregation. Rest of the aspects such as transportation decisions and models for transportation and distribution we will see in the next lecture.